So let's take a step back and actually compare the differences between aldehydes and ketones. So I've talked about Mount Carbonyl, which I'll reemphasize again. And this is a thing. Imagine these carbonyls on a mountain. Things at the top of the mountain are the most reactive. And near the top of the mountain is the aldehyde. Now, why is the aldehyde more reactive than a ketone, which is right below it? So think about hyperconjugation. A ketone, right, has sigma bonds. It can have sigma bonds 2 bonds away. So they can be pushing electron density towards that. Now, it's not resonance, right? It's not resonance. But they can be inductively pushing electrons, like electron density, like hyperconjugation. And because an aldehyde only has one of those possibilities, because it has an H on one side, right? It's only 1 bond away. An aldehyde is necessarily more reactive, because when you push electrons towards something, that makes this less delta plus, right? You're pushing electron density towards it. That makes it less reactive, less electrophilic. Also, sterics, right? It's easier to react with an aldehyde because this is just a little H. It's easier to react with the aldehyde carbon of the carbonyl than a ketone that has 2 R groups to get to that carbon of the carbonyl. So we've done some carbonyl additions with nucleophiles. We've made alcohols. And those are easier. Those are basic conditions where the nucleophile adds in, right? We make a tetrahedral intermediate. Those are basic conditions. But now I want to introduce acidic conditions. So now we're in the realm of having H+. So what happens with an aldehyde or ketone in acidic conditions? Well, the first step is a protonation. All right? If we have H+ around, that's my best electrophile. That's a really good electrophile. So that's going to react with the lone pair, right, of a ketone or aldehyde. And that protonates it. Why did we do that? That makes this more reactive. How does it make it more reactive? Well, if you look at the final product, right, there's a plus charge on the oxygen. But you know, just because there's a plus charge there, where's it really electron deficient at? It's really electron deficient at the H and at this carbon. And you can see that by a resonance structure, right? This resonance form, these electrons go up. You can see that the carbon of the carbonyl group is pretty reactive. Right? So we use the acid to make this more electrophilic. Once it's more reactive, we can add in a nucleophile. Now notice the nucleophile, can the nucleophile have a negative charge? Well, no. Why? Because we're in acidic conditions. We're in acidic conditions. So a lot of times the nucleophile could be something like another alcohol or an amine. Something with lone pairs, probably, right? Those lone pairs are what react. Not a negative charge, though. Once that adds in, the plus charge now is on the nucleophile that reacted, right, because it lost electrons. And then a lot of times you regenerate. These are acid catalyzed. You regenerate. So what else we made here was H3O+, which is another way of just drawing H+. Right? So these are acid catalyzed a lot of times. And catalyst, of course, gives you an alternate pathway for reaction, usually with lower activation energies, and it's always regenerated. So you're not done with this mechanism until you've regenerated the catalyst. Alternatively, if you're in basic conditions, in this case, you're having a reactive nucleophile. So you usually have a nucleophile with a negative charge, right? Negative charge, basic conditions. And in that case, the first step is actually the nucleophile reacting with the carbonyl, the carbon of the carbonyl, doing that addition. You've done these before. And you make a tetrahedral intermediate. When you make a tetrahedral intermediate, what do? You ask yourself, do I have a good leaving group? And if you don't, you go to the next step, which is protonation, and you get these alcohols. We've done this a number of different ways, right? With aldehydes, ketones, and esters, actually, too. You learn about esters in the basic conditions. So in basic conditions, addition happens first, and then protonation. In acidic conditions, protonation happens first, then addition. And then usually you have to regenerate your acid in those conditions. So, aldehydes and ketones can do a lot of reactions. But the mechanisms for most of these falls into one of two categories. Acidic conditions or basic conditions. Those are two things we just reviewed. So reduction, right, that usually involves H minus. What kind of conditions will that be? That would be basic. Reaction with Grignard reagents. What would that be? Well, Grignards have a carbanion. Those would be basic conditions. Hydration can actually be both, and we'll talk a little bit about that. Acidic and basic. Addition of cyanide, so something like Cn minus, that would be basic conditions, right? Negative charge carbon. And again, acetal, we're going to get a little bit of both. Imine, enamine, also a little bit of both. But what we'll learn and talk about first for most of these is acidic conditions. Same with up here. We'll learn both, but we're going to start with acidic for these. And that's what you've seen before. An example you've already seen. The sodium borohydride, lithium aluminum hydride. H minus, right, that's basic. The first step is what? Addition. You add in. You make a tetrahedral intermediate. What do you ask yourself? Does it have a good leaving group? It doesn't. Protonation. And that works for lithium aluminum hydride as well. Same idea. Basic conditions, right? Taking an aldehyde, making it into an alcohol. We also know how to do Grignards. Again, review. C minus, the Grignard reacts. We do the addition. Do we have any good leaving groups? No. We do protonation. Another way to make alcohols. Take an aldehyde or ketone and turn them into alcohols with Grignard. Basic conditions. Nucleophillic addition. Good. That's not a hydride. That's alkyl. I would say Grignard. Same mechanism as a hydride. So something new we're going to do is a hydration, which is a way of adding water, right? Just like it sounds. Hydration of carbonyls. And it makes this gem diol, which is a way of fancy saying two alcohols on one carbon. And you can do these in acidic or basic conditions. Acidic or basic conditions. And guess what? Depending on the conditions, will tend to tell us what mechanism we use. So this one, this is the basic mechanism. So without looking at this, if I say basic mechanism, you know the first step is going to be addition to the carbonyl, and the second step will have to be protonation. So then let's look at this. If I add in a strong nucleophile OH minus, it adds in to the electrophilic carbon of the carbonyl, breaks the pi bond. We make a tetrahedral intermediate. Do I have a good leaving group? Some might say OH is a good leaving group, but notice this is an equilibrium. Right? It's an equilibrium. If I add enough of this, I'll shift equilibrium over to this way. Right? I'll shift equilibrium. So then I get to here, this tetrahedral intermediate, and the last step will be protonation. Right? Using water. And I've regenerated OH minus. And this is a gem diol. So that's basic conditions. What would acidic conditions look like? What's going to be my first step? Protonation. So I'll protonate, make this a more reactive carbon of the carbonyl. I have a weak nucleophile, no negative charges. In this case, water comes in, reacts. I make this tetrahedral intermediate. And in this case, I would be, then the water, more water comes in and regenerates this acid as catalyst. This is an acid catalyzed process. Which of course means there's going to be the final step will be what? Regenerating the catalyst. Right? You have to regenerate the catalyst. Acidic mechanisms, protonation, addition, and then usually a final deprotonation just to regenerate the catalyst.